Good morning to everyone. Today we will discuss the fundamentals of photovoltaic technology. Photovoltaic technology is one of the most widely used renewable energy technologies for converting sunlight directly into electrical energy. In this presentation, we will understand the basic components of a photovoltaic system, the formation of solar modules and arrays, and the photovoltaic reactions that generate electricity. The photovoltaic cell is the fundamental building block of any solar power system. It is an electrical device that converts sunlight directly into direct current or direct DC electricity through the photovoltaic effect. When sunlight falls on the cell, electrical energy is generated without any moving parts. This direct conversion process makes solar energy a clean and reliable source of power. A single photovoltaic cell produces only a small amount of voltage and current. Therefore, multiple cells are connected together to form a module. These cells can be connected in series, parallel, or a combination of both. In a series connection, the voltages of the cells are added together while the current remains the same. The arrangement helps achieve the required output voltage for practical applications. The photovoltaic cells are enclosed within the protective module structure to shield them from environmental conditions such as rain, dust, wind, and temperature variations. One or more modules connected together form a panel. Several panels or modules connected electrically and mounted on a supporting structure form a photovoltaic array. The total power generated by the array depends mainly on solar irradiation and operating temperature. To improve the electrical conductivity of silicon, a process called doping is used. During doping, specific impurities such as boron and phosphorus are added to the silicon crystal. These impurities alter the electrical properties of silicon and increase its ability to conduct charge carriers. Doping is an essential step in the fabrication of solar cells because it enables the creation of regions with different electrical characteristics. In a crystalline silicon solar cell, one side of the silicon wafer is doped with boron, creating a P-type region with positive charge carriers called holes. The opposite side is doped with phosphorus, creating an N-type region rich in free electrons. The boundary formed between these two regions is called the PN junction. This junction is the heart of the solar cell and plays a critical role in electricity generation. When sunlight strikes the solar cell, photons transfer energy to electrons present in the semiconductor material. These electrons gain sufficient energy and become free from their atomic bonds. The electric field present at the PN junction drives these free electrons toward the N side and holes toward the P side. This separation of charge carriers prevents recombination and enables the generation of electrical energy. As more electrons are released and separated by the electric field, an electrical potential difference develops across the solar cell when an external circuit is connected. These electrons flow through the metal contacts and the external load before returning to the cell. This movement of electrons constitutes the electric current which can be used to power electrical devices. An important characteristic of a solar cell is that its voltage output remains almost constant regardless of the cell size. However, the current produced depends directly on the surface area exposed to sunlight. A larger cell can absorb more solar energy and therefore generates a higher current. As a result, increasing the cell area increases the power output of the solar cell. The photovoltaic effect and the operation of a solar cell, they show the structure of the p-type and n-type layers, the formation of the depletion region, the movement of the electrons and holes under sunlight, and the generation of electric current through an external circuit. Understanding this helps visualize how sunlight is converted to useful electrical energy. Design of a standalone PV system. Estimating the PV system sizing includes estimating electrical loads, sizing and specifying batteries, sizing and specifying array, specifying a controller, sizing and specifying an inverter. The types of batteries are lead acid battery, liquid wintered. The lead acid battery is again classified into liquid wintered and shielded. Second one is alkaline batteries. The alkaline batteries are again classified into nickel cadmium and nickel iron. Battery specifications are days of autonomy, battery capacity, rate and depth of discharge, life expectancy, environmental conditions, price and warranty, maintenance schedule. Thank you. In this presentation, we learned about the photovoltaic cells, modules, panels and arrays. We also discussed the doping process, the formation of the PN junction and the photovoltaic effect responsible for electricity generation. These concepts form the foundation of solar photovoltaic energy conversion and are essential for understanding modern renewable energy systems. Once again, thank you.